Hello, in part number 6 we'll look into the system components, namely electric machines, frequency converters, gearboxes and transformers. Welcome. Electric machines. They're very versatile in design, form, size, shape and so on. So on this slide we have a collection of just large electric machines. And still you see they are very different in shape. You will see some similarities in them, but still you can understand that they are very different. And this is the beauty and the complexity of working with electric machines, as you will see. For example, this quite bulky element on top of the machine. It looks quite big. What is this? It is cooling element. You see it here. The heat exchanger is basically put on top of the electric machines. So air is going through the windings and the cores of the machine, and then it is being cooled down by the heat exchanger. This is one design variant. Another design variant is just put some cooling liquid inside the machine. So you can see it here. The liquid is coming in here and going out here. And in addition we have air circulating like that. So then this machine doesn't have a heat exchanger on top here, so it looks quite smaller than the previous one, but that means the heat exchanger is somewhere else. It's another unit somewhere else which is bringing in cold liquid, cold water for example, and gets out hot one. So this was on cooling of electric machines. So the electric machines are of course different not only by cooling system, but also by type. And this is the biggest difference actually. So you see, for example, that permanent magnet machines are considerably more compact than induction machines. This can be almost like half size of the induction machine. Moreover, efficiency of permanent magnet machines is higher than what we have for induction. This is the important advantage of permanent magnet machines. But of course, permanent magnet machines and induction machines are just two types, and there are many more types. What we have in DriveConstructor, we also have synchronous reluctance machines, these ones. So if you look at the rotor of these motors, you will see they're quite different from induction machines. So here we have induction machines with squirrel cage motor, and here is the reluctance motor of synchronous reluctance machine. So the difference we get by using synchronous reluctance versus the induction one is losses in the rotor. So efficiency of synchronous reluctance is higher than the efficiency of induction machine. In DriveConstructor we have just these three electric machine types. Again, permanent magnet machines, induction machines and synchronous reluctance machines. It will be enough to understand the differences between the machines. But of course there are many more types of electric machines, like for example switched reluctance machines, synchronous machines, DC machines, and some more types. But we have to be selective here and not to make it too wide, the search space, so to speak, when designing systems. So these three will be enough. Another special thing about electric machines is efficiency classes. So you can see output power is here and efficiency is there. And these are the efficiency classes from the lowest one, IE1, to the highest one, IE4. So industry is now quite strict on producing high efficient motors. That's why these classes has been introduced. Another thing is protection classes. We touched this already, when talking about putting machines or putting some components into the containers or in some other places in the previous parts of the lecture, but now we can look closer to into the IP classes. So it's actually how well the electric machine is protected from the environment, from, for example, dust or some particles like sand or something else getting into the machine. So will it go through or will it not? The same for water. So will some drops of water, splashes of water or fog will be critical for the machine or not? So this is quite useful knowledge to be aware of these efficiency classes. Some more things about electric machines. This is so-called intermediate operation. So when we first load the machine, it has some torque, and then there is no load. So the machine is just resting, it is cooling down. And then we have this cycle again. So it's like cyclic operation. And what is happening when we have cyclic operation? The temperature can go up and down in the machine. So if it does not pass certain limit, doesn't go over it, the machine will survive, it will be operating okay. But if you would go above this limit with your temperature, then insulation can be irreversibly damaged. Now to frequency converters. Frequency converters, they may have internal cooling, like this fan we see here, built into the frequency converter, or alternatively it can be water cooled. Then water would be coming from some other place. So frequency converter can be cooled by these two types. Usually there can be actually a combination of two, but usually it's either air cooling or liquid cooling, like water cooling. Also we should remember that frequency converters can be losing some of the performances when operated at high elevations. So then the loadability of the frequency converter goes down, because at higher altitudes like 2, 3, 4 kilometers, the air is less dense, and then cooling like that will not have the same effect as on the sea level, at the sea level. Also, frequency converters can handle different overloads, like what is shown here. This is small 10% overload, and in this case it's like 50% overload. So the same frequency converter can be either run with this kind of overload when the overload itself is quite close to the rated current, and the same converter can be run like that when the rated current and the converter current are a little bit further from each other. So you can read more on that in DriveConstructor to understand the details of this. Now a little bit on system design. So frequency converters, when we have them between the grid and the electric machine, they generate some harmonics which can negatively affect the grid. So that's why we need to have filters between the frequency converters and the grid. The same is true for protecting the electric machine from the frequency converter. So there can be filters needed, like this sinus filter, for example, between the frequency converter and the electric machines. Frequency converters are quite dangerous for both what is before them and after them, the grid and the electric machine, because frequency converters are switching devices, so they produce spikes of voltages and currents in both directions. So this should be taken into account. There can be quite interesting aspects and trade-offs in system design, and we'll now look into one of them. So, as you know, there can be a phase shift between the waveforms of voltage and current being sent to the electric machine from the grid or the frequency converter. So we can talk about an electrical angle between terminal voltage and current. And the same angle is actually defining some powers. So a real power here is what is used for energy conversion from electrical to mechanical. It is sort of a useful power. But there is also reactive power, which is basically just a pulsing power between the grid and the electric machine, or the frequency converter and the electric machine. So it's more or less parasitic power, which we usually do not need. And apparent power is in a way a product of these two, the real and the reactive ones. Power factor is actually equal to cos sinus phi if we have sinusoidal currents and voltages. So it is more complex to define power factor if the voltage and current waveforms are distorted. Then we need to add some harmonic components, some harmonic coefficients. But to simplify the case, power factor is almost the same as cos phi, cosinus phi. And power factor usually is a bit lower than 1. So it can go down, of course, to 0.6, but usually it is in the range indicated on this slide. For machines with permanent magnets, we can during the design stage, we can affect the power factor of cos phi. If we put more magnets into our design, then usually power factor will be higher for this machine. Less magnets, then it will be lower. And field weakening capability of the permanent magnet machine will be affected by the number of magnets. So if the magnetic field is dominated by magnets, so it is made by magnets and not by the currents coming from the stator, so this machine will be more difficult to field weaken and run at high speeds. So this machine will be less suitable for high speed operation, for over speeds, let's call it more correctly, for over speeds, but it will have higher power factor. So what does it mean to have a higher power factor in practice? So that means that we will consume less or have less reactive power. So reactive power is designated with the red arrows here. So this is a pulsing reactive power. You can see it is bidirectional. It is not producing any mechanical power in the end, just sort of disturbing in a way. And the green arrows designate real power or active power, which is good power because we are using it to convert into mechanical. So what is this two systems drawings indicating? When we have high power factor, then we have low reactive power, like here. So our machine is bigger in this case than in the second case, but our frequency converter is smaller because overall current is smaller. So you see, to have high power factor, we need to design our machine to be bigger, bulkier. So we put more effective materials in it, but we save money on the frequency converter. And maybe you know that the cost of an electric machine and a frequency converter, sometimes they are comparable. So like having 10% larger machine can be equivalent to having, say, 20% smaller frequency converter. So then the system cost will be more or less the same. So by this example, we see there are quite complex trade-offs in the system design, and you can affect how your system will look like by designing your electric machine in a different way or just using a different electric machine. So that's why we should look at the currents and power factor and efficiency, of course, of the electric machine together with a frequency converter. Let's talk about the dimensioning again. From part number 3 of this lecture, you remember that the general rule is that the system curve should be above the load curve. So the torque of the system should be always above the torque of the load. So in this, on this slide, we have a conveyor as the example of load, and conveyors, they have constant torque load. So it's like a flat horizontal line. So what the slide is also showing us that there can be not just the main torque, but there can be some overloads. So the conveyor suddenly can be overloaded because it's a big stone on it or something like that. It is, if it is a mining industry, it can be stuck because of something is stuck on the belt of the conveyor and so on. So it may have different sorts of overloads, and overloads will vary in amplitude and duration. So you see CO, this torque is 1 degree of overload, which can be some 30 seconds, for example, due to some conditions. And TCS is like ultimate overload that can happen. It is very short term, but it can be double torque. So that means our system should be capable of handling all these overloads. And usually, so if we call our combination, the combination of an electric machine and frequency converter a drive, so the drive will have a rated curve. This one, this is the continuous torque the system can deliver. And it may have temporary overload capabilities, like these two levels, corresponding to the possible overloads of the conveyor in this case. So the second torque, or the first overload level, this one, can be, for example, 50% higher torque, possible in just 30 seconds or 1 minute. And the higher level of overload can be just for 2 seconds. Usually the frequency converter is a limiting factor here, because otherwise the switches will overload if we overload it for longer than 2-3 seconds. So this should be kept in mind. And then we should say that not only continuous torque of the system should be above the load torque, but also these other two overload curves or lines of the system, its torque capability should also match the load. So you can be okay on 2 of them, but maybe fail on the 3rd overload level. So this is important to remember. The second thing that this diagram is showing, that we can have different cases depending on the cooling solution for our motor. So here in case number 1, we see the torque capability is reducing with the reduced speeds. And this is because it is being cooled with a shaft-mounted fan, this particular motor. If we have independent cooling, then our allowability curve of the system is starting basically from 0 speed right on the rated torque. And that means that our conveyor can be run at lower speeds in case number 2 compared to case number 1. So here you see N1 is starting at a higher speed. And also when it comes to overspeed, so if you want, on the right hand side picture, run our conveyor with a little bit of overspeed, 5 to 10% higher than overspeed, we can also do that. But we should remember that the conveyor torque should be under the system loadability torque. So you see there may be not 1 but 4 or 5 points which we need to check. So main rated torque, long-term overload torque, short-term high overload torque, low speed and high speed. So it's quite a lot of things to look at together. Now to gearboxes. On these 2 pictures it is the same gearbox, but on the right hand side picture it is without the housing. Gearboxes are quite complex components. So this particular gearbox is just one stage gearbox. So it is reducing the speed maybe with the ratio 1 to 6. And well, there will be a shaft on this side and a propeller. This is marine gearbox. And here will be connected a diesel engine. And on this small shaft there will be electrical machine, a small one, for generating some power while the gearbox is running. And it also can be used in case the diesel engine got failed. So then it is like take me home function on it. Okay, so gearboxes can of course have more than one stage. It can be 2, 3 and even more stages in the gearbox. In DriveConstructor we have included up to 3 stages. So then you can imagine how many cogwheels will be in such gearbox if it is like 3-stage gearbox. The art of designing and building, manufacturing of the gearboxes is equally great as the art of designing electric machines. So it's not a simple component as maybe some people might think. So it's not just speed reducer or speed multiplier. It's a real device which can cost as much as the electric machine, sometimes even more, can weigh quite a lot. So we electrical engineers, of course, we are not designing them. We shouldn't probably know how to design gearboxes, but we definitely should know how to use them. So what are the mechanical interfaces of gearboxes, types of the gearboxes, of course, ratios, stages, and efficiency. So what is happening with the efficiency of the gearbox, for example, at partial load. So all this knowledge we need to obtain. We understand quite well efficiency of individual system components, like of an electrical machine. But what if the electrical machine is put together with a gearbox and then frequency converter and transformer to form the total system? So what is the efficiency of the total system? Well, the answer is efficiency of the system is the product of efficiencies of its components. It's easy. But what is special here? Some of the components, like the gearbox, for example, when it consists of several gear stages, we then should remember each stage will have its own efficiency. So efficiency of a gearbox is the product of efficiency of the stages. And that means that 3-stage gearbox will have lower efficiency than, for example, 1-stage gearbox. So this is one thing to remember. Second thing to remember is that efficiency at the full load and at partial loads, they differ. So efficiency is falling with the falling load on the gearbox. And the same is actually usually more or less true for an electric machine. In this example, on the right-hand side, we have put together on the same chart several systems. So the comparison was done for the application of tidal turbine. So TT is tidal turbine. And the power of tidal turbine is going up like that with increasing speed of the speed of rotation of the blades. And we can see that the system with this 3-stage gearbox has quite a low efficiency compared to the others. That's because the second and the third stage of the gearbox, they bring down the overall efficiency of the gearbox and of the total system. So here it is quite clear that DD, which is direct drive, has the best efficiency across the speed and load range in this particular system. So this is important to remember. Partial load efficiency and number of stages in the gearbox. We did once a study on efficiencies of the drivetrains of wind turbines, and this information was published in a paper. So it is quite similar to the study on the previous slide. So what we see here is the curve for low speed permanent magnet synchronous generator. Low speed means it is without any gearbox, it is a direct drive, has the highest efficiency in the wind speed between 7 and 11 RPM in this particular example, even though its efficiency is lower than some other efficiencies here in this area at the wind speed close to rated wind speed for this turbine. But the point is that energy chart for wind turbine looks like that. So most of the energy produced by wind turbine is produced at reduced or partial speeds here. So that means it is very good for the system when it has efficiency maximum here in this region where most of the time the turbine is operating most of the time. So then direct drive is really good choice here and for this particular case. and actually direct drives are more and more used in wind turbine industry. So like 20-30 years ago, usually they would have 3-stage gearbox with an induction generator, but today it is more like direct drive with permanent magnet synchronous generator the wind companies would use. On this slide, we're trying to make a direct benchmark of the two competing systems. 2-stage gearbox plus permanent magnet generator versus 3-stage gearbox with squirrel cage induction generator. And the power flow diagram is quite a good visualization of the differences between the two systems. So we have blades, then gearbox, electric generator, cable and frequency converter, and the grid in this on this diagram. And we see the power is flowing from left to the right, from the blades to the grid. So if we use 2-stage gearbox and permanent magnet generator, then we do not need this third stage, and we do not have any losses in this stage because it is not there, as it would be with a synchronous machine. So this is point number 1, where the permanent magnet generator with 2-stage gear wins. Secondly, in the electric machine itself, if we do not have squirrel cage, if we instead have magnets, then we will not have any losses in the squirrel cage of the rotor. So this is the second point where permanent magnet system is winning. Since we also have high efficiency in PM machines, even copper losses are lower. So it's a third point where is win something. And actually, because we didn't have the losses in point number 1 and point number 2, we didn't have losses in stage 3 and in the electric machine. So the overall load on the machine is lower. So that's why actually the winding losses can be low as well, because we just pump less power through it. The same is true for the cable, because the overall efficiency of the components here was higher and the losses were lower. We bring lower current through the cable. So it's a point number 4 where PM system is winning. And the same logic is applicable for the inverter losses. Lower current, lower losses. So it's point number 5. So you see that altogether we win quite a lot by just going from the system with 3-stage gear and squirrel cage induction generator over to the system based on permanent magnet machine. So I hope it is a good visualization. As the result of the advantages described on the previous slide, the system with permanent magnet generator will be generating slightly higher power than the squirrel cage induction generator system with 3-stage gearbox. It is not very visible here at the load close to rated. But here on this chart it is visible. It's like maybe 5-10% more power generated in each cycle. So these cycles are actually tide cycles, so they are several hours. So during the day the tide reverse, so, and it is like going through 0 point. It turns the direction, the water, but for power generation it doesn't matter. You just rotate your turbine in a different direction. So the power is always like a positive product of this process. So you see that it really matters what components we use for our systems. It matters for power production directly, whether it is a wind turbine or a tidal turbine. Now a bit about hardcore industrial applications. So you see from the pictures the conveyors and the respective drives for the conveyors. Quite extreme things, quite harsh environment. It's a lot of dust and mud and water and whatever. So the components of the system should be really chosen with the right protection degree and with the right ability to withstand vibrations and shocks and so on. So what is typical for conveyors? It is overloads, quite high overloads. So here we see that the overload can be like 50% and even like a double overload. And also we need to talk about duty cycles here. So duty cycle is a cycle when you have on-off operation. So for some time you have your motor and the rest of the system on because you suddenly need to move something, and then you're off, it is just resting. So what is happening to the temperature then in the motor? First of all, it is going up and down, up and down. It's important to make sure that it is not going up like that. That is like never stops before the insulation burns. So it should be balanced thermally. Well, so duty cycles, they can be, of course, with a different duration. So it can be like 25%, 50, 75, and everything in between, and above 75 and below 25, of course. But the duty cycle is just showing how much you're running the system and how much it is resting and cooling down. And the lifetime of the system will be defined by the duty cycle, as well as by many other factors. A pump is usually thought as the simplest application for the variable speed drive for the power conversion system, but they are not as simple actually, because there are quite many types of the pumps, and these types of pumps are characterized by different load curves and different behavior, different efficiencies. So on this slide I just have a collection of several types: progressive cavity pump, positive displacement, screw pump, and centrifugal pump. Of course, centrifugal pumps, they are most common, so they used like in water supply, central heating systems, and so on. So they are very widely used. But when we come to industry, so like chemical industry, oil industry, and so on, then we will meet more and more for different variants or types of the pumps. What is important to remember that the load curves for the pumps may be different. So this is centrifugal pump, and this is positive displacement pump. And you see that in the first case, for centrifugal, the load curve is quadratic, while for the positive displacement pump type, it is constant torque, like it would be for a conveyor, for example. So usually we think that the pump is a quadratic load curve, but remember, it is not always like that. Sometimes the pumps, they behave like something else, like not pump here. Also, efficiency of the pump, hydraulic efficiency, I mean, varies also with the load of the pump, the flow of the pump, and head of the pump. So this is where we need to look at the system as a whole. So not only efficiency of the frequency converter and the motor and transformer and so on, but also the mechanism efficiency, pump efficiency, if we want really to optimize the whole system. Now a brief look into the marine application, the winch application. So actually winches, of course, they are used everywhere. So a winch and a hoist, it is more or less the same thing. This is when you are lifting something up and lowering it down. What is special with the winch application is that when we coil the wire on a drum, like on these two pictures, we start from one radius of the drum, and after we have coiled quite a lot of wire on it, the radius is different, so it's a larger radius or larger diameter of the surface on which we are coiling the wire. And actually this is the thing that is defining quite special character of the load and overload curves of the winch. So you see it is falling down with speed and time. So you should really look into these equations and understand what is happening with the winch when the linear speed is set and you start coiling on. Then to keep the same linear speed, you need to change the rotational speed of your winch when you start getting on the drum a lot of wire, when your diameter of the drum has increased. So then obviously you are reducing the rotational speed, and this is why the torque speed curve of a winch is like that. So actually not only winches have these strange curves, it's also all kinds of winders. For example, in pulp and paper industry, there's a lot of machines like that. So it's quite interesting application. You will find it in DriveConstructor. Of course, there exist quite many of different winch designs, and this is just one example. And here, what is interesting is that the electric machine is integrated inside the winch drum. So it is here, like hidden inside the winch drum. And here we have a brake on the left-hand side. So here, stator is internal, and the magnets are at the periphery of the machine. So the magnets are on the rotor, which is inner part of the drum. It's quite interesting application. Just a few words about inertia in the drivetrain. It's quite critical thing in many of the applications. And inertia in the drivetrain will be defined by the gearbox. So you should really read up on this in the DriveConstructor textbook. Because the gearbox can play sometimes positive role in the dynamics of the drivetrain and sometimes negative role, depending what application we have and what situation we have. So sometimes, for example, the gearbox can save us in case the propeller is going to run away. So the brake, for example, was not engaged, or the generator failed and the counter torque disappeared, so the blades start rotating faster and it can damage the wind turbine. The blades can just collapse and fly away. So then it is the gearbox can really be helpful in braking the wind turbine. In some other situation, in the winch situation, for example, if we are dragging a net behind the vessel and the net is stuck, then the gearbox can play a negative role. So it will sort of make the dynamics of the system slower, and you just break the winch or just your wire collapses. So this situation should be analyzed with special expressions. And here in this table is just an example of analysis when we choose different gearboxes with different number of stages, and we see what is happening to the inertia and what will be the reaction speed and so on. And it is important where we have the brake in the system. So on this drawing, we have it between the gearbox and the generator. So it is like at the high speed of the gearbox. But we could have it, for example, here between the thrust bearing and the gearbox. So then the system dynamics would be different in these two cases, and the brake size would be different in these two cases. So please look into this theory and try to solve the tasks, go through the exercises on this. Well, this was the last slide in part number 6. Thank you for watching these videos. I realize that's a lot of information, but we need to just go through this briefly and then probably read the textbook and look at the examples there and look at the exercises, try DriveConstructor, and maybe you come back to these lectures again. So usually you should go through the same material several times in order to understand and remember everything. Thank you for watching again.